So as chemists, we often need to know the number of atoms in a sample of a particular mass. Why do we care about the number of atoms? Because chemical processes happen between particles. When you make a molecule of water, it's 2 atoms of hydrogen and 1 atom of oxygen. It's between individual particles, and so we need to know how many particles. Well, you can't count them, so what we do is we count them by weighing them. And we do this with things in everyday life as well. We count large numbers of objects by weighing them. In a factory where they're making a box of, such and such, I don't know. My example maker is on the fritz today. They'll weigh the box. They know the mass of each individual object, and so they'll weigh the box, and based on that, they can tell how many objects are in there. Do you think they actually count the airsoft pellets in a canister of airsoft pellets? There's like 1,000 in there. Nobody counts those. They know how much one weighs, and so they put in enough that it's the right mass. They seal it up and ship it off. They usually put in a little bit of extra so that if you are crazy and count them, you won't get too upset because you only got 999. They do this with many consumer products as well. I shouldn't tell you this story, but I'm going to tell you anyway. So when one of my kids was 2, he got into a bottle of Target brand acetaminophen. So it was a brand new package. He's 2, right? He opened the box. He took off the shrink wrap seal. He took off the childproof cap. He took off the foil lid, and he pulled the cotton out. And they're all over the floor in the kitchen. Right? Like, oh no. And just to top it all off, he was sick. He had a fever. And so I had just given him a dose of children's Tylenol, right? And so I come in here and I'm like, oh no, right? So I'm thinking, well, it was a brand new bottle. I'll just count the tablets, and then I'll be able to tell if he took any, right? So it's supposed to have 100 in it. There's 102. So who's to say there's not 103 or 104? And a kid that size, even a double dose of acetaminophen can do permanent liver damage, right? And so, like, oh my goodness. Why were there 102 in there? Because they don't fill those bottles by actually counting the pills. They do it by weight. And they're going to err on the side of too many so that you don't get upset if you actually count them, right? Because then you would feel cheated if there was only 98 in there. Like, oh, you make a big stink, right?
Do you think they do the same thing for controlled drugs?
When you go to a pharmacy and get a prescription, they do actually count them. Yeah, they do. They have a counting machine.
Only because we have to go to the DEA, like whenever we get like tramadol.
Mm-hmm.
When it comes in, we get bottles of thousands.
Right.
And then we're off because of them. Then obviously.
I think when they ship those large bottles to the pharmacy, those are probably counted as well. But over-the-counter stuff, they don't count them. Because it's not that important, right? So why, it's more effort to have the machinery to count things automatically, and that makes the stuff cost more. And so they're trying to make everything, less expensive, so we'll buy it. And so they don't count things like that. So he was fine. This is kind of a life lesson here. So just don't keep acetaminophen in your house if you have small children. Ibuprofen works much better. So we had to take him to the ER and get a blood test. I was afraid they were going to pump his stomach. Do a blood test, and they can see if they've had too much, and then they can give him an antidote. If you don't take that precaution and they did get too much, the first sign is a couple days later when their liver begins to fail, and at that point there's nothing you can do. I learned this from poison control. And then a couple years later I had to call poison control again because the next child, who was 2, got into the bottle of children's ibuprofen, the liquid. So yeah, no more Tylenol in the house after that thing. So he drank some of it. It tastes good. Oh my goodness. So I called poison control again. Well, it turns out that he could have drunk the whole bottle and at most he'd have an upset stomach and maybe throw up. It's a lot safer. So that's just my 2 cents on that. And that took a lot of time, but okay. We count things by weighing them. And we also use some counting units for things, right? When you go to the donut store, you don't say, I want 57 donuts, right? You tell them how many dozen donuts you want. And a dozen is 12. You have a dozen donuts, a dozen people, a dozen feet, a dozen anything is just 12 of that thing, right? Another unit is a gross. It may sound kind of gross, but a gross. A gross is a dozen. So that's 144 objects. Another unit of counting is a ream. A ream of paper is 500 sheets of paper. Okay, so we have these counting units in everyday life. So chemists have their own counting unit. It's called a mole. It's not mole. It's not a sauce. It's not a little animal with poor eyesight. Mole. And it has an abbreviation, which I think is stupid because it's so short anyway, but this is the abbreviation and we got to go along. So the abbreviation is MOL. We often refer to this as the chemist's dozen because it's like a dozen. It's a particular number of things. This unit we're going to use a lot, and it's sometimes hard for students to get their brains around it. I know you saw this unit in your prerequisite class, but it didn't maybe make sense. So I want it to make sense now. A mole is whatever amount of that thing that contains 6.02214 times 10 to the 23rd particles. Now that may seem like kind of a random number. We don't need to remember all of those digits. 6.022 times 10 to the 23rd will be good enough. So a mole is that number of particles. That number is called Avogadro's number in honor of the guy whose work led to what that number was. So 1 mole of anything is 6.02214 times 10 to the 23rd units of that thing. Just like a dozen is 12. The chemist's dozen is a number of things. It's just a really weird number, not a nice number like 12. So this number of atoms or molecules gives us a reasonable amount of material. So 22 copper pennies, that's approximately 1 mole of copper atoms. So you can hold 22 pennies in your hand, right? It's small enough to handle, but large enough to see. So it's a nice amount. 1 tablespoon of water is approximately 1 mole of water molecules. So a mole of atoms or molecules is a reasonable sized amount of stuff. So I have to tell you another story, sorry. So 6.022 times 10 to the 23rd, is, it's kind of a special number for chemists. 6.022 times 10 to the 23rd. And you should memorize that. So in October, chemists celebrate Mole Day. It's October 23rd. 1023. It's like Pi Day or May the 4th, right? So October 23rd, and technically it goes from 6:02 a.m. to 6:02 p.m. But we usually don't get hung up on that. And so my second son, no, he's not the second one, he's the 4th son. My 4th son, the one who drank the ibuprofen, was born on Mole Day. And my husband's a chemist and I'm a chemist, and that was just like the most awesome thing. So his birthday is October 23rd, and he weighed 10 pounds and he was 23.5 inches long. The only thing that could have been more perfect was if he had been born at 6:02. I worked on it, but it just didn't happen. And we actually had this very brief discussion. Should we give him the middle name Avogadro? No. So we didn't. But anyway, he's my mole baby, October 23rd. So a mole, 6.022 times 10 to the 23rd, things. How did this number come about? Why do we use that number? That's because that value is equal to the number of carbon atoms in exactly 12 grams of pure carbon-12. An atomic mass unit is 1/12 the mass of a carbon-12 atom. And so this gives us a relationship between grams and numbers of atoms, and it also pulls in average atomic mass. So 12 grams of carbon is a mole of carbon atoms. It's Avogadro's number of carbon atoms. So when we convert between moles and numbers of atoms, it's just like converting between dozens of eggs and numbers of eggs. But instead of using 12 eggs per dozen, we're using 6.022 times 10 to the 23rd things per mole. The chemist doesn't. So this is our conversion factor. 1 mole equals 6.02 times 10 to the 23rd atoms. So you can put moles on top and atoms on the bottom, or you can tip it upside down. And we'll do these conversions using dimensional analysis, put the units in, and we don't need to remember, do I multiply or divide? The units tell us what to do. So a pure silver ring contains 2.80 times 10 to the 22 silver atoms. How many moles of silver are in that ring? And moles of silver atoms. So we identify our number here. We're given one number, 2.80 times 10 to the 22nd atoms. And then the question is, how many moles? So we're converting atoms to moles. And that could be done in one step, just like you could convert number of eggs into numbers of dozens of eggs. Okay? So we're just following dimensional analysis. 2.80 times 10 to the 22 atoms. We have one arrow, so we have one conversion factor, one fraction here. I want moles on top and atoms on the bottom because I want the units to work out. The relationship between moles and atoms is that 1 mole is a certain number of atoms. Just like 1 dozen is 12 eggs, or 12 whatever, 1 mole is Avogadro's number of things, 6.022 times 10 to the 23rd. Now you need to be careful when you do this on your calculator that you're using scientific notation correctly. Otherwise you're going to end up with a really, really huge number. So get your calculator out and actually do this. So you should have either an EE button or an EXP button. Some calculators have a times 10 to the n button, and you may have to be careful with those. But what you're going to do is you're going to do 2.80 EE 23. Sorry, 22. EE stands for times 10 to the. So we've got 2.80 and times 10 to the, we just press EE. There's no times, there's no 10. It's all in the EE. It's an abbreviation. Times 10 to the 22. And then we do times 1 divided by 6.022 EE 23 equals. And I come up with this number, 0464 96181. And the unit would be moles, M-O-L. Not M, that's meters, M-O-L. Always have to think about significant figures. This number has 3 significant figures. In scientific notation, all the digits before the times sign are significant. The 10 to the 22nd, that's the place holding zeros, so those are not. So we got 3 sig figs here. Avogadro's number is not exact. We do know it to more digits, but we don't really need them here. So that has 4 significant figures. So we're going to round this to 3 sig figs. And remember that leading zeros don't count. So this is our 3rd significant figure. And so we're going to say, well, it's 0.465. No, I did that wrong. I lost my 0. 0.0465 moles. Now, if you ended up with a really big number, that's because you're not communicating with your calculator correctly. Please talk to me in lab and we'll get that straightened out. I'll give your calculator a talking to and tell it to behave. Because it's your calculator's fault. It's not your fault, it's your calculator's fault. We just have to straighten it out a little bit. Any questions? Gosh, this goes on and on and on. We're just going to do it. Okay. So that's between numbers of atoms and moles. It's still not getting a mass to a number ratio. So we need to use the mass of 1 mole of atoms. So the mass of a mole of atoms is the molar mass. It's the mass of a mole of whatever that is. And this is where the definition of Avogadro's number comes in so nicely. An element's molar mass in grams per mole is numerically equal to the element's atomic mass in atomic mass units, AMUs. What? So aluminum, each aluminum atom on average has an average mass of 26.98 atomic mass units. That tells me that 1 mole of those weigh 26.98 grams. So the numbers on the periodic table below the element symbols, there's no unit on there, right? You can use that as the average mass of an atom, then the unit's atomic mass units. Or it's the mass of 1 mole, and then the unit is grams. It's beautiful. So a mole of aluminum, mole of carbon, mole of helium. Always the same number of atoms, but they don't weigh the same amount. Because here's a helium atom. It's little. Carbon's kind of medium-sized here, and aluminum atoms are much bigger. They're heavier. If you have the same number of heavy things, it's going to weigh more. A dozen cars is going to weigh more than a dozen donuts. But it's the same number. Yeah, but the cars are a lot bigger. Okay? So to convert between grams and moles, you just use that molar mass. It's on the periodic table. So for carbon, 12.01 grams is equal to 1 mole. We can express that this way, 12.01 grams of carbon per mole, or 1 mole per 12.01 grams of carbon. It's on the periodic table. Let's calculate the amount of copper in moles in a 35.8 gram sheet of pure copper. Again, dimensional analysis. Just deal with the units. So we're given one number. That's right, that must be where we start. 35.8 grams of copper. And we're supposed to find how many moles. So grams to moles is something we can do in one step. But we need to know the molar mass of copper. It's not given in the problem, so we look on the periodic table. So if we look on this periodic table, it says 63.546. That's the number under copper on the table. That's grams of copper per mole of copper. So that's what we need for conversion. So we're going to set this equation up using the units first and then putting in numbers, 35.8 grams times and a line. And we've got one step here, grams to moles. So we've got moles on top and we've got grams on the bottom. Just doing dimensional analysis, trying to get the units to work out. After we've got the units in place, we find the numbers and the units tell us where to put them. So I have this relationship. I can use it right side up or I can use it upside down. But the 63.546 is grams. And so I'm going to put that in the denominator where grams is, 63.546. And per mole, that would be 1 mole. So 35.8 divided by 63.546 equals. And I'm tired of writing down all those messy digits, so I'm going to think about sig figs. This starting number has 3 significant figures. This molar mass has 5. These are not exact numbers. This has 5. So my answer should have 3. So 0.563. There's the 3 sig figs. Write down 2 extra digits, and the unit is mole. Then round it for the final answer, 0.563 moles. Here I used the full molar mass that was on the periodic table at hand. That is always fine. It is not fine to round this to a whole number. Don't round that to 64. That's going to mess things up. What I will do in lecture, much of the time, is I will use molar masses that are rounded to 4 significant figures, because I have a whole bunch of them memorized, and it's just so much faster. Do not round to fewer than 4 significant figures. If your periodic table has 5 or 6 and you don't want to mess with them, you have my permission to round it to 4, but don't go less than that, okay? Always keep at least 4. Questions? Yeah.
So if we was calculate the amount of copper atoms, then we just add the next step, which would be the compound.
Yeah, that's a good question. Do we have a problem like that? Let's just go back to this. So if they wanted to know the number of atoms, we could take moles and use Avogadro's number to get the number of atoms. We could also do it in one step, because for copper, 63.546 grams equals 1 mole, which equals Avogadro's number of atoms. So if this equals this, which equals this, then 63.546 grams equals this many atoms. And so you could use that as a conversion factor. You can do it in 2 steps or in 1 step. Do whichever makes more sense to you. Any other questions? So this is, the conceptual plan for doing a problem like this. Here we're talking about going from grams of an element to moles of an element to numbers of atoms. I always did it in 3 steps, and then, some books show it in 2 steps, and I'm like, oh, yeah, well, that's kind of cool. It's better, though, to do the thing that you always remember what to do with. So it kind of depends on how your brain works. But here's is this the last? No, what the heck? Okay, there's only 2 left. I'm tired of this too. How many carbon atoms are there in a 1.3 carat diamond? Diamonds are a form of pure carbon, and they give us this relationship. A carat is 0.2 grams because I don't remember that. I wouldn't expect you to know that. That'd be even hard to look up. Okay, so we read the problem. We're going to write down the number that they gave us. This only has 1 number. Got to use the pen. Okay, 1.3 carats. And I'm going to write out carat because I don't want to confuse it with cups or anything. So that's what I'm given, and I'm asked for atoms. So I'm going to try to get to atoms over here. Do I know how many atoms are in a carat of diamond? No. Okay, well, they gave me this, right? So I can convert the carats to grams. Okay, grams are a little more friendly to chemists. So grams. And then how do I get from grams of carbon to atoms of carbon? Yeah, most of us would go grams to moles to atoms. So grams to moles to atoms. You can skip directly from grams to atoms, but I'm not going to do that here. So that's our plan, our path, and then we just follow it. Figuring out the path is the hard part. The rest of it is just, some tedious stuff. 1.3 carats. I look at my path, there's three arrows, so I'm going to have 3 factors. Carats to grams, to moles, to atoms. I just copy them down. The first unit comes to the denominator, so it'll cancel out. And grams goes down here, so it cancels out. And moles goes down here, so it cancels out. Isn't that pretty? Now I put numbers in. Well, this one's given to me. 1 carat is 0.20 grams. So I have carats on the bottom. 1 carat is equal to 0.20 grams. What's on the top of the line has to be equal to what's on the bottom of the line. And then I've got moles and grams, and I've got atoms and moles. Well, this one is always the same. A mole is Avogadro's number of things. 6.022 times 10 to the 23rd. So 1 mole is 6.022 times 10 to the 23rd atoms. Oops, 23. The relationship between moles and grams we find on the periodic table. So for carbon, on this periodic table, it shows 12.0108. Well, I remember that as 12.01. See, what happens here is this has 2 sig figs, this has 2 sig figs. If I express this with 4 sig figs, it's not going to limit the number of significant figures in my answer. That's what we want to avoid. We don't want our molar mass to be causing us to lose sig figs. So I'm going to use 12.01 because that's what I remember. 12.01 grams of carbon in 1 mole of carbon. That's going to be different for each element. So we've got everything in place. We have 1.3 times 0.2 divided by 12.01 times 6.022 EE23 equals. Do we expect this to be a big number? Yeah, a 1.3 carat diamond is pretty big, right? We can definitely see it. Anything you can see has a ginormous number of atoms. This should have 2 sig figs, so I'm going to write down 2 extras. 1.303 times 10 to the 22 atoms. And then I'll round that as 1.3 times 10 to the 22 atoms of carbon. Any questions? If you ever do a problem where you're finding a number of atoms and you come up with less than 1, like if you got 10 to the minus 22, it's not possible. It's like with people, right? You can't have less than 1 person living in a house. It's either nobody or 1 or more. Yes?
The first factor in the middle, 1 mole of carbon over
12.01
grams of carbon.
Any other questions? Okay. So this is the sort of problem that we do to 1A students that we don't do to Chem 3A students. This requires a little bit of thinking. So a titanium cube has 2.86 times 10 to the 23rd atoms. What's the edge length of the cube? Who cares? But it's here, so we got to do it. The density of titanium is 4.50 grams per cubic centimeter. They gave us the density, which is nice because it gives us a clue that, oh, hey, maybe we need to use that instead of making us figure it out and go look it up, so it could be worse. Okay, so let's write down what we've got. 2.86 times 10 to the 23rd atoms. And then we've got this density, 4.50. Write this as a vertical fraction. Grams divided by cubic centimeters. and I'm trying to find the edge length of the cube. So we're going to have to think about this. Sometimes it helps to draw a picture. So I've got a cube, and so I'm going to call the edge length L. It's very creative, right? So the edges of this are all the same. So for a cube, we know that the volume is equal to the edge length cubed. So if I'm trying to find L, I could do that if I know what the volume is. So I need to find a volume. What unit of volume might be convenient in this problem? How about this one? Cubic centimeters. It doesn't specify the unit for the edge length, so then we can choose whatever we think is the easiest. So I need to find the volume in cubic centimeters, and then I can use the equation. So we're using dimensional analysis and an equation. It happens a lot. Well, how do I get from atoms to cubic centimeters? Probably have to use this density. Density gives me the ability to convert between grams and cubic centimeters. So if I had grams, I could get to cubic centimeters. Now this is looking a little better. Atoms to grams. How do we do that? We need Avogadro's number, right? So we can use Avogadro's number to convert number of atoms to moles, and then the molar mass to convert moles to grams. What we're going to find is that the unit mole is going to be in the middle of a lot of calculations. Moles in the middle. Reminds me of the TV show Malcolm in the Middle. Right? Moles in the middle. So if you're getting lost, try putting moles in the middle somewhere and see if that helps. .86 times 10 to the 23rd atoms. I've got 3 arrows, 3 fractions. The first one's going to be moles, and the second one's going to be grams, and the third one is going to be cubic centimeters. Atoms to moles to grams to cubic centimeters. I get a little tired of going forward, so sometimes I go backwards, canceling out my units. Units first, then numbers. Yes?
How did you come up with the map?
Well, I know that I need to find the length of a cube. The question is, how did I do the map? I need to find the length of the cube. And I know for a cube that the volume is the length cubed. So if I know the volume, I can use this equation. So I have to somehow get this number of atoms into a volume unit. And that is suggested to me by that density. Does that help? And really, the path is the hard part. Okay, so this was just handed to me, not exactly on a silver platter, but it handed to me on a white screen. So let's put that in here. That would be 1 cubic centimeter and 4.50 grams. Okay? Moles and atoms, this is always the same. Just like a dozen is always 12. 1 mole is always Avogadro's number. And then the relationship between grams and moles is on the periodic table. So titanium, where did you go? There you are. Number 22, 47.867. 47.867 grams is 1 mole. It's molar mass, it's the mass of a mole. So the number always goes with the grams, not with the mole. So 2.86 EE23 divided by 6.022 EE23 times 47.867 divided by 4.50 equals, I'm going to keep track of my significant figures. My starting number had 3. My density has 3. Avogadro's number has 4, my molar mass had 5, so this is going to have 3 sig figs. 5.05, and then I want to write down the next 2 extra ones because that's not my final answer. That is not the edge length of the cube. That's the volume of the cube, right? So this is the volume. So now I have to use a little bit of algebra. So the length cubed is equal to the volume. If I want to know what L is, I need to take the cube root of both sides. So L equals the cube root of the volume. So it's the cube root of 5.0518 cubic centimeters. Oops, I need to do that. And then you have to figure out how to make your calculator do that. I'm working that out with mine right now. So on the TI-30X Pro, you want to press 3 and then the root button, and then I'm going to put the 5.0518 in there and press equals. We'll say this also has 3 significant figures. So 1.71, and there's the 5.8. The unit would be centimeters now, and so we'll round that to 1.72 centimeters. If you need help with your calculator, I'd be happy to help you during lab.
Which calculator do you have?
36X Pro, the TI-36X Pro. Any questions? And there's the end of chapter 2.